I'm going to move the lecture along here a little bit. Now, there was a problem apparently with the last video. I was just taking a look at that. And for the first hour and a half or so of class, it didn't record the video. It recorded the audio. So what I've done, I went through and looked at an older lecture, which is the same. It's called lecture 11, I think. So the lecture I'm referring to is lecture 7, which was last Wednesday. And it's a continuous thin line of charge. So it's an important video to be able to see the diagram. And I went back and found an older lecture that hasn't been deleted from Zoom yet. And it was a pretty good lecture, and it's very clear, and it's the same lecture. So it's a thin line of charge, and then I think I do a ring of charge, and I put the timestamps in the lecture 7 information so that you can easily go to lecture 11 of spring 20 and find those lectures. So go ahead and take a look at that, and what's going on with this? Doing that. Okay. Yeah. So there's one other example that I will think. Actually, this, you know what? There's another example that's a really great example to do, and it's a thin semicircle of charge, but it's also in lecture 20. I think the timestamp, in fact, that the timestamp for that one is 1 hour and 7 minutes or something like that. And then the thin ring, which is a full circle, is 2 hours and 4 minutes. And the beginning of the lecture deals with the thin line of charge. So I think those lectures are pretty clear, and I'm going to leave it to that lecture to handle that example. Now, I want to move on with what this is week 5, and we should be moving on to something called Gauss's law. Oh, by the way, yeah, something called Gauss's law, which is it's actually a mathematical concept. Gauss was, I think, a Swiss physicist or mathematician who introduced this, but it turns out it's very practical applications in physics. And again, Gauss's law is well, it's a concept that allows us to find electric fields, but doing it in a way that is not so rigorous like Coulomb's law. So you notice with Coulomb's law, we have the basically a brute force method of calculating the electric field in a region surrounding a charge distribution. And you know, it's very specific, it's very detailed, and that's awesome. You know, we really want to know how to use Coulomb's law, but you know, if we can avoid all the mathematics, you know, why not? And also, it's not just about avoiding mathematics. Gauss's law shows aspects of the electric field and the physics associated with the electric, you know, a field that is just really interesting and also characteristic of the universe. Remember, 4 themes that I have in this class are technique, specificity, perspective, and symmetry. And Gauss's law exploits symmetry of certain types of distributions in such a way that's pretty magnificent, I think, and revealing aspects of the universe that are not so obvious. And then we can use them, use that to find the value of the field. So let's see if we can derive Gauss's law. So Carl Friedrich Gauss, I said he was Swiss. What does it say here? Gauss, well, I don't really give an expose. It just basically says what I just said. But before we actually derive Gauss's law, we have to introduce something called a concept called flux, electrostatic flux specifically. But flux is a concept that doesn't just apply to electrostatics, it also applies to gravity. In fact, there is a gravitational, as I've been showing you, gravitational analogies to all of the formulae that we've been developing associated with electrostatics. There is a parallel, usually, some sort of parallel with the universal law of gravity. And Gauss's law is no exception. There's actually a Gauss's law for gravity, which while I'm deriving, I might go ahead, might as well go ahead and do that for you and do both of them. But let me go with Gauss's law for it. First, we have to discuss the concept of flux, as I was stating. Now, if there were students in class, this is the point where I would ask you if you've ever heard of the term flux before, and if so, in what context? And many students, well, of a certain generation, might mention the Back to the Future with the infamous flux capacitor, which was the engine of that car that got the scientist's name, the physicist's name in that movie, but who made the car that took Michael J. Fox's character back to the future. Some sort of, maybe it was just flux capacitor or something, but very scientific name, which actually, well, I'm not sure if we've made cars that can do that, but essentially what I think that was referring to was the idea that, in physics, oftentimes we want to hold charge and we can use that charge. We want to control charge and manipulate it. And there's a certain physical engineering process that when you're creating high magnetic fields, you need a lot of voltage. And one way to do that is to store that voltage on capacitors and then release that voltage at a certain time. And it causes a very extreme high magnetic field if the device is engineered so that all of the fields superimpose at a specific point. And magnetism, I'm sure, probably has something to do with as well as time travel, with as well as electrostatics with time travel. So I'm not sure if anybody's working on something like that. If that name had any kind of relevance to something that people were actually doing, but the idea of creating high magnetic fields with magnetic flux associated with capacitors, maybe that's somehow where they got the name from. Actually, that's part of the research that I did when I was working on my PhD, working at the High Magnetic Field Laboratory at Los Alamos Labs, and now based at Florida State in Tallahassee. Anyway, that was a diversion, but point is that the name sounds real cool, but it actually is somewhat associated with at least making high magnetic fields. And I don't know anything about time travel research, but I'm guessing that magnetic fields and large fluxes, high flux of magnetic field is probably associated with that, as well as gravity, probably all fields. But at any rate, let's talk about electrostatic flux. The term flux really, another analogy for the term flux is flow. In fact, that's the definition that I usually give in class, which has a nice little ring to it. And I think it's very easy for students to remember that definition. Flux is flow. But specifically, it's the flow of a field through some sort of surface, through the cross-sectional area of a surface. So flux is flow through a surface, meaning surface area. It is the amount of flow of a, in our case, field through a cross-sectional area. Now, to help guide your intuition with that, another area I think that the term flux is often used practically or pragmatically is with water flowing through whatever, canals, pipes. And in that case, we're not really talking about a field. Usually it's the velocity of the water and times maybe cross-sectional area. I'm not sure. I have to think about it. Actually, I think we cover that when we do Bernoulli's equation. So the continuity equation. But the term is not really referred to as flux, so to speak, but it is essentially kind of an analogy. It's the flow of water through a pipe. And you can imagine that as you decrease and increase the cross-sectional area of the pipe, the amount of the volume of water flow and changes. And another way that you might think of it is, again, air. When we're looking at the weather person on the news at night, they usually have a flow which indicates high and low pressure, but you also see the arrows flowing. The high and low pressure of the air dictates how the air flows. And you have what's called contour lines. The contour lines are indicative of the flow of the air, wind, which usually corresponds from high pressure to low pressure. That air will flow into a high pressure means a high density of air molecules per unit volume. Low pressure is lower, right? So if you got a really dense area of air, it would want to flow into an area that is low temperature, low pressure. So the values of the air pressure are kind of consistent with, you see the flow lines flowing from high pressure to low pressure. So that's another case where we're using lines. In this case, it will be field lines that represent essentially the field strength. And in our case, when you have, for the weather, whenever the contour lines are closer together, that's a way of qualitatively indicating that the pressure is higher. And if you were to look in that area on that map, weather map, where they have the pressure, the values of the pressure, it's going to be higher in the places where the contour lines are closer together. The line density is greater. So what we say is that, we've already said this, actually, we did this a week ago, that when we looked at field lines are proportional to the density of the field strength. And so in our case now, we're going to be looking at fields that will change, and as they change, the field strength will be proportional to the line density, the density of the lines per unit area, per unit volume. And as those lines flow and interact with objects in the area, like, anything, any kind of maybe a metal ball, or that we might poles or anything really, then those fields, you can think of them as flowing through the surface of the objects. And you know that does happen, right? When you're on your phone, you have an electromagnetic wave. Of course, we're talking about static fields here. An electromagnetic wave is not a static field, but still it's a field. And when you have poor reception, that's because maybe you walk into a concrete building or something like that. That's because the electric field has a bit more difficulty flowing through the concrete of the wall as opposed to when you're outside. But that flow through the cross section of the building would be considered flux. Essentially, that's it. It's the definition of the field strength, E, flowing through some cross-sectional area of an object. And we quantify that in the following way. The symbol for flux is a capital phi from the Greek symbols. So actually, capital, yeah, capital phi. So by definition, flux, put it here. Maybe usually a small e or something like that. So that's the symbol for flux. Lowercase e or higher case e, I guess, doesn't matter. I'll put a higher case e. We'll have something similar for magnetic. So this is electrostatic flux. There's also magnetic flux. It's not a vector, it's a scalar quantity, which implies to you that, which leads to, here's the definition actually. It's defined as the integral of the dot product between the electric field and the surface through which the electric field is flowing of the surface for a material or an object. Now I'm going to put dA there because dA, we have to look at, sometimes the field is not constant over the surface, so you have to evaluate the electric field over the infinitesimal area and then add up all the areas, and that will give you the total. Now, in the case, and so that's definition. Now, we can look at that another way. Obviously, we'll do problems where we take the dot product and we work through that. But sometimes the electric field is constant over the surface. When you have a constant field, for example, and it hits a flat surface, then, well, it hits a surface and it's constant over the surface, then it's regardless, it can conform to the symmetry. But at any rate, when the field is constant, then it comes out of the integral. And if it's going through, I'll illustrate this. If the field goes through, then the angle between the angle, well, I guess we need to, actually, let me get to that in a minute. Yeah, before I talk about the angle, let me illustrate geometrical implications of flux. So I need some definitions here. The number n is going to be the number of field lines in a region, capital N. N. A is the magnitude of some cross-sectional area. And also here we have to generally or up till now, you've probably thought of area as a scalar quantity. For the example, if I have a circle, the area of a circle is pi r squared. The area of a rectangular object, length times width of a box, its length, the length is the same. So if the length is a, then the area of any surface would be a squared. Well, we have to redefine area now as a vector quantity. And it's not really that difficult to do. Redefining area as a vector does require, though, that we attribute some way of determining the direction associated with this, with an area, a surface area. And it's very simple. If I have a surface, a flat surface like this circular circular piece of paper, then it has two surfaces, the front and the back. And we define the direction of an area associated with the direction that is perpendicular to that surface. So for side one, the direction would be, I guess, to your left. Well, one side, the side that I'm pointing to here. And for the other side, the side is the direction of that area is pointing to your right. And the magnitude of both sides would be pi r squared, but their directions would be opposite one another. So the direction of a cross-sectional area is the direction that is perpendicular to the surface. How do I say this? We must assign a direction. We must redefine area as a vector. And the direction of a cross-sectional area then is going to be perpendicular to the surface. So we'll say A then vector equals the magnitude A times the, and I'm going to make this like a unit vector N, which is, represents the perpendicular to the surface. And we'll have some pictures here in a minute to illustrate. But this is just a unit vector. The direction of a cross-section is the direction that is perpendicular to the surface of that cross-section. And by cross section, I mean area. So, usually that term is referred to when you're taking the area of a three-dimensional figure. So let's say that I have a ball, right? A ball, and I slice the ball, then it's going to, the cross section will be the circular shape associated, well, circular, or it depends. It could be or elliptical, depending on how I slice it, right? Yeah. But that is considered the cross section. But when you're dealing with a flat surface, that flat surface, I mean, I'm just still using that term. Like here, if I take a cross section of a thin flat surface, you're going to get a line, right? It's not really, I mean, if I cut it, then the place where I cut it now for a two-dimensional figure will be a line. For a three-dimensional figure, you're going to get a surface. If you cut a two-dimensional thin figure, which is what this is kind of representing, you're going to get a line. But when I'm saying cross section, I'm just referring to the flat area part of whatever object we're talking about. So only a two-dimensional or three-dimensional figure can have a cross section. And technically, for a two-dimensional, the whole object is the cross section itself. So we're not talking about slicing that or anything. Anyway, cross section just means surface area. So the direction of a cross section is the direction that is perpendicular to the surface of that cross section. Yes. So yeah, if I have some figure here, like well, let's use a flat that was a circular piece of thing. Let's use sure, let's do the thing. I'll represent here this circular figure. I'm going to try to draw a three-dimensional representation. So because we need to look at I'll do both. So I can look at it straight on, or I can look at it kind of askew like this. And if it's straight on, then the area, the magnitude of my area, well, the magnitude of area, regardless, is going to be pi r squared, where r is the radius of this thing. And let's do it like this. Okay, so this distance is r. And as I told you, if I have this area, it's flat on the surface like this, then the direction is perpendicular to that surface. So if I'm looking straight on, the unit vector n that's associated with that area is going to point straight out toward me. And remember, with our notation, a circle with a dot in it represents a vector out of the board. So the magnitude would be a, and if I represented the vector a, then a vector would be equal to basically pi r squared times n unit vector, where n unit vector is pointing out toward me. So again, this magnitude is pi r squared. So that none of the formulas that you've known is going to change. It's just that now we have to associate a direction with it. So if this were a flat, like looking at a kind of a side view, I don't know how would that be, like an oval? It would look oval shaped from the side, and maybe kind of like, sorry, I'm not the greatest freehand artist here. So if I took it, where is it? Oh, you know, and then kind of turned it kind of like this, you're looking at it, it's going to look something like that, right? And so now the area vector A is going to, it's got to be perpendicular to the surface, right? So it's going to look something like this. Pointing straight up like that. That's going to be A. And again, remember the unit vector, it's unit vector, right? So that's the N right here. And again, the total vector A is this guy, where A is the magnitude of A is pi r squared. So from this point on, for the rest of the, intermediate physics, that means 38 and 39, always think of vector now, of area as a vector quantity from this point on, always. Now, that's a flat surface. For a closed surface, we have a convention. For a closed surface, now in this case, I didn't really establish positive and I mean, the back side of this also has an area vector that points in the opposite direction, right? So one obviously is the negative of the other. Now, in this case, since I'm not really working a problem and I'm just defining A, I don't want to confuse that by putting on the opposite vector of the other side. I'll just say that this side that I chose to illustrate was arbitrary. So, you could flip it over, be the same thing, But if I'm actually working a problem, I need to define a positive direction. And I will leave that to specific problems when I have a flat surface. But another very interesting case is closed surfaces. In other words, the little box that I showed here any box has what, 6 sides? Yeah, 6 sides. And each of those sides is a surface. And as I've just shown you, it has a vector, area vector associated with it, each side. For a closed surface, we take the convention that the positive direction of the area of any side points away from the center, away from the inside of the closed surface. So for a box, any of these 6 sides, this is the positive area associated with that side, the area vector that points away from the closed portion, away from the inside. For this side, and I've numbered them. Let me take this off. I've numbered the sides, 1, 2, 3, 4, 5, and side 6. So for my little echo dot box here, that's become so handy with my class demonstration in electrostatics. All of the sides, if I were to represent the vectors, they would be vectors pointing away from the surface, and the magnitude of the vectors would be a squared, all of them. But they would have different direction for obvious reasons. For a sphere, a spherical surface, which is just one surface, the area of a sphere is 4 pi r squared, 4 pi r squared. And the direction is perpendicular to the surface at any point, right? As we just stated. So therefore, the direction really is, there's several, I guess. Well, you would have to use spherical coordinates. So in spherical coordinates, Cartesian coordinates, it's all over the place, right? Infinite number of directions. But in spherical coordinates, the direction would be along the radial direction. For spherical coordinates, you might remember the coordinates are r, the radial vector, theta, the azimuthal vector, and then phi, the spherical, the azimuthal direction, and then phi, the actually I just think the symbols usually people use phi for the azimuthal, and then theta for the spherical um, angle, the angle relative to the vertical. Anyway, so even though from a Cartesian point of view, that looks like very many directions, from a spherical coordinate point of view, it's just one direction. It's the radial direction, radially away from the center of the sphere. So yeah, area is a vector and it points perpendicular to the surface. Even if you have a multi-surface object, then each of those individual surfaces would have a unit vector associated with them. So let's say that. So for a closed surface, yeah, or a closed surface, A always points away from the inside. Doesn't necessarily have to be the center. It's only going to be the center if you have high symmetry, but definitely from the inside of the closed surface. Points away from the inside of the closed surface. Um, so in the example of a sphere, we have a couple of examples here. Sphere. I'll put some three-dimensionality on that. Looking directly at the side, if I have a tangent that hits that surface at various points, then A for this portion is going to be pointing like that, right, perpendicular to that side. And here A is like this, that guy. For a box, as we'll see, each of these has an A associated with its various sides. So here A is going to, and again, just to emphasize that it's perpendicular, I can do this little square thing that we like to do with perpendicular lines. I don't know, here I have to draw it three-dimensionally, something like that. But all of these sides have their A associated with them, something like that. And I can denote, maybe this is different sides, but A1, 2, in general, A3, so on and so forth. Yeah, I'll just, let's say a rectangular figure here. Okay, that's clear and legible. Yes, 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 yes. So, coming back to this definition, what does that mean? Well, now let's take a surface and let's just use a different geometrical figure now, a flat rectangular figure, basically a flat piece of paper or a rectangular piece of paper. And let's immerse it within an electric field. Now, hello, Libra gang, how are you? Let me pin this thing to the surface. I can get maybe this guy. Libra gang, are you there? I guess you'll come in whenever you need to. But yeah, we're saying that we have a flat surface here. And actually, I think I might have to, my apartment, they're going to come in here and do some work. So you might hear a knock on the door. I think I have the noise canceling earphones in. So there you go. That's better. I think the noise canceling is kicked in now. I actually cut off the, still learning how to use these. So let's see. Yeah, so that's off. And that's on. So when they come in, I'll make sure I have these noise canceling. I'm going to keep it off just so I can hear the door. But when they come in, I'll activate it so it shouldn't bother us too much. Actually, just one moment, please.
Good morning, Professor.
Hello, Libra gang. How are you?
I'm good. How are you?
I'm well. So
Yeah,
I got some
sorry if I
feedback
missed.
going on. So let me see if I can work this out. What is that feedback here? What were you saying?
Somehow I missed to submit the lab one.
Okay.
I don't know.
No worries. Just send me an email and let me know what and I can reopen it for you so that you can get it sent in. Okay.
All right, thank you, sir.
Yeah, no worries. And yes. Yeah. So we are moving on here with moving along here with the electric field considerations, and I'm discussing something. I'm introducing something today called Gauss's law, but which is another way of calculating electric fields other than using the methods that we have in calculating Coulomb's law. And so that's what we're discussing today, this week, actually. Now, in order to derive Gauss's law, we have to first introduce something called flux, electrostatic flux. This is the definition of flux mathematically. And what I'm doing right now is explaining qualitatively what flux is. And we started out by talking about the idea that flux is flow. It's the flow of an electric field through essentially a surface. Now, when we think of electric fields flowing, the analogy that I gave you were contour line. If you look earlier in the lecture, contour lines like on a weather map, how the lines show the flow of the air, negotiating the air pressure. Those lines are contour lines, which can be analogous to field lines for a field. And so we can think of the electric field, which we've looked at for a point charge. We know that it points out radially, and we've looked at the field of a dipole. One way of thinking about those field lines is that it's the flow of, I don't know, if you want to define what electric field is, I guess you could define it in terms of the energy in the field or something like that. We do that when we talk about energy coming from the sun and we get a suntan or we out in the sun. So in the same way, you can think of that, or even light. Light is an electromagnetic wave that's flowing. It's not a static field, but it's a field. And when it hits you, you feel the energy. So when we're talking about static fields flowing through space, that's really what we mean. It's kind of like thinking of it in the same way we think of the rays of the sun coming from the sun. And they can flow through a window pane. They can flow into your skin, and be absorbed by the melanin in your skin. So that's what we mean when we say that a field is flowing through space. It's not moving, it's static, but the direction that it moves is kind of like the contour lines, on a weather map, or, you can think of that as the currents in a river too. Like if you look on a map of the sea, sometimes you can see the certain, flow of the river based on, or the ocean or the sea based on different pressure and temperature of the water. So that's what we mean. And now I've digressed just a bit, because in this formula, E represents the electric field, dA represents a differential surface element. So I've been talking about the fact that up until now, you've only thought about area as a scalar quantity. Area of a sphere, 4 pi r squared, area of a rectangular surface, length times width. But in order to understand flux properly, we have to redefine area as a vector quantity. And the way that we have done that is, I've just said that that area is, the direction is always going to be perpendicular to the surface. So for this rectangular figure, its area is the length times the width, but it has two sides. And so, come on in. Hey, come on in, man. Yeah, come to do the door. Yeah. So you're not gonna disturb me. I've got a class going on right now, but I've got some earpieces that cancel the noise. Yeah, it'll cancel the noise. Oh, you're good. You're good. I'm gonna put these things on. I think it'll cancel the noise. Do you need me is that clear enough for you over there? Everything? Okay, yeah, just move. All right, cool. I want to go ahead and put these things on there. So that should be canceling out any background noise. As I was saying, I don't know what I left off, but two sides. So the direction for this side is going to be a vector that's perpendicular to that side. And the direction of this side is like perpendicular to that side. And so I had explained that there. Now we made this point about closed surfaces. For example, if you take a rectangular figure, which has 6 sides, each of those sides has a direction associated with its area, and the positive direction for a closed surface is always the direction that points away from the inside of the surface, the inside of the closed surface. So that's area. That's area. Now, what I was about to do is take this surface and immerse it in an external field, so that now we can see how the electric field and the surface area interacts for a single surface or for a closed surface. Let's do a single surface first, this guy. So I'm going to take this and I'm going to represent this piece of paper. I'm going to kind of put it askew like that, maybe something like that. and we'll have an electric field. Now let's assume that our electric field is a constant field, which means that it is going to be pointing linearly. So, well, linearly, pointing from your left to your right. I'm just going to have a constant field in some area of space, some region of space, like so. That's pointing, you know. Now I'm going to go ahead and draw. I'm trying to draw this two-dimensionally or three-dimensionally, so that's a little bit difficult with the lines, but whatever. I think I might be able to. So if I take, yeah, actually I should have drawn the paper first. Let me do that. Just I need to do that so I can gauge. So I'm just going to take this piece of paper and we're going to look at it kind of like from a three-dimensional perspective. That's kind of how I'm going to try to draw it. So might look something like yeah, so maybe it's more like this. We're looking at the back like that. And I'm going to have some vectors, some field vectors. And I don't know what kind of field it is, just whatever. Maybe E field, I guess. Sure. Make it an E field. So the field lines are going, they're going to go through like this. So it's going to hit from that side, but then it would have to hit on the back side and then go through. So it might look something like that and then come out over here. That's kind of making a three-dimensional representation. Again, hits there, goes through somewhere, and then comes out maybe here, that side, and then here, goes through, comes out, that, and so on and so forth. Okay, that's definitely given a three-dimensional kind of I hope, it looks somewhat three-dimensional. So this is the electric field E, but the surface is still, which is E. But the surface has its own, and I've tried to draw this in such a way that it's hard to see it. I mean, we might have to do a side view, but like if the field lines, like the field lines are not hitting the surface such that they are perpendicular, right? So if the field lines are pointing like this, and the piece of paper is like this, then you can see that like I have to kind of put it through it, but I can't really do it from the side. But basically, this field is not perpendicular. If it were perpendicular, it would be kind of like that to the surface, but it's like this, right? So I've tried to make that a little bit clear here. It's more clear when I do it from the side. But if I draw the area vector associated with the surface, it is perpendicular. So if the field is not perpendicular, then the area vector is going to make an angle with the field as that field cuts through that surface. So maybe this guy would represent the area vector. I don't know. I have it here. Maybe it's. I should have exaggerated even more. I don't know how to do that. I'll have it sort of kind of pointing like that. Okay, well, yeah, it's kind of perpendicular out in that direction, right? Or yeah, so maybe that would be like here slightly. So maybe that's A. And so we got some sort of angle here, right there, with the surface. I'm going to make a side view and exaggerate it so that, again, E is horizontal, pointing from your left to right. And my surface, I'm going to, put it at an angle like this. So if that's the case, the side view of a surface is here. Like so. But my area vector is horizontal and cuts through like this. Sorry, my E vector, my electric field vector. It's horizontal and it cuts through like that. So that from the side view, and let's make this, let's indicate that this is a side view. Side view. This is a 3D view. From the side view, this area vector, the green vector there, is going to point up like, it's got to be perpendicular to the surface, right? So that guy looks like this. That's A. So the area, you know what? Gotta. I've been doing some work in the apartment, as I mentioned. I think I'm gonna be painting, so I need to open a window here to kind of put down some primer. I might actually put on a mask myself. You don't mind? I think it's not gonna, because I got the earpieces in. I don't think it's gonna affect my voice that much. From your point of view. Testing, testing. So Liebegong, can you still hear me okay? Or Liebegong, are you there?
Yes, I can hear you, Professor.
Okay, thank you. Thank you. All right. So as I was saying, we have the area vector here for this surface. And remember, this is just the side view of this piece of paper. So you would just only, you would just be able to see the little line really. And the area vector is perpendicular to that. And the electric field, I'm only drawing one line of the electric field, but the electric field permeates the entire space. Yeah, I can draw a few more just so you're clear about that. The field lines now, are parallel. They're permeating the space. Okay. for the whole thing. And we only need to have one comparison. We only need to take one. We could draw the area vector anywhere on the surface, but we don't need to keep drawing it. Just draw one line there. Yeah. And so A and E are going to make an angle relative to one another, which is this angle here. Oh, that's phi or theta. So in the dot, now here's the intuition about this guy, about this, why this definition makes sense, why we write the dot product. The argument of the integral is the dot product between E and A. Now dA here is just a differential area, but in a case like this, where the electric field is constant over the surface, then E basically comes out of the integral, and you just have the integral of E, or E times the integral of dA. That's the thing that I wanted to start saying over there, but I realized that I needed to give kind of a pictorial representation so that you can understand what I'm actually talking about, and also what comes next in terms of the result. And so we're there now. So let's come back to this definition over here. I'm going to erase this and leave that definition here. So in this particular, so a couple things. One, we already know well, maybe this is a point where I should review the geometrical implications of a dot product. Remember, I told you from last semester, well, we've done that. Last semester, we know what a dot product is. I can review it really quickly here. But essentially, a dot product is telling you the amount of one vector that is essentially parallel to the other vector. So just review dot product real quick. Geometrical implications of dot product. Let's say this. If I have a vector A and B, which make an angle relative to one another, so let's say this is vector A here, and then I have a larger vector, a longer vector B, and let's say the origins are at the same place. Then I can I can, if I take a dot product, what I can see here is that A dot B. So if I drop a perpendicular here from A to B, then I'm going to make a right triangle. Like so. And so we can see that this portion here, that portion just from geometry, we know that that portion is A times the cosine of theta, because it's the adjacent side of that right triangle. And of course, theta is the angle between A and B. That's theta. So, you know, the magnitude of A dot B by definition, that's equal to A dot B is equal to the magnitude of A times the magnitude of B times the cosine of the angle between them. But one way to think about this is that if you group A and cosine A, cosine theta together, you can think of the dot product as B times the component of A that is parallel to B, which is equal to A cosine theta. Right. So I guess I could do it like this, A cosine theta, which I can call that A parallel. All right, so essentially, when you take the dot product between those vectors, you pick out the part of A that is parallel to B. Or in its relative, right? It's vice versa. If I were to project A out, project the line that is parallel to A out, I could also drop a perpendicular from B to A. Like that. And then this portion here, that would be B cosine theta. So I could also regroup this as just A times B cosine theta, and an equal representation of A dot B would be A times B parallel. All of A times B parallel. All those are the same thing, just different perspectives, again, perspective, different perspectives of the same dot product. We can think of it either as the part of A that is parallel to B, or we can think of the dot product as the part of B that's parallel to A. Either way, they're in the same direction. So that is a property of the dot product itself. As I told you last semester, or for those of you who had me last semester, oftentimes in physics, when we write mathematical or physical definitions, quantities, the properties, the physics properties of the quantity become really fume. Our fumes in here from that stuff they're doing. Wait, how did they get the D1023 so fast? Take a break here in a minute. What was I saying? Yeah. So the mathematical properties become properties or characteristics of the physical quantity itself. And so we have that here in this case with flux. Because if we now bring that back to this situation here, I know it's kind of small, I don't want to come, but flux is flow, right? So what we really want is the part of the electric field that flows through the surface that is tantamount to the part of the electric field that is parallel to the A vector associated with that surface. Because in order for something to go through a surface, it's got to be perpendicular to the surface. If it's parallel to the surface, it just flows. Like, think about water, right? If this were like, if I had a hose and this were like a chain mail type of thing, chain mail meaning that it was just like a wire, like chicken wire. So if I made this chicken wire and I had a hose, if I take the water and I allow the water to it's kind of counterintuitive because it's parallel to the surface, but parallel to the surface means perpendicular to the cross-sectional area vector because the area vector is perpendicular to the surface. But if the water is just dripping down parallel, then it's not going through, right? If I take the water hose and I just, point it so that it's just drops down, it's the velocity vector is, I guess, parallel to the surface, then the water is going to flow down the surface. Flowing down the surface is not flowing through the surface. In order for it to flow through the surface, I would either have to turn the paper so that it's flat so that the water moves down, or I could take the water hose and, make it perpendicular to the surface from this point of view and spray it through, and it would go through, right? The chicken wire. But if that's the case, it's going to be parallel to A because A is also perpendicular. So whatever, if I get a vector field that is parallel to A, that means that vector field is going through the surface because, like A, it's perpendicular to the surface. So in order to figure out how much of E is going through this surface, what we need to do is execute this dot product, E dot A, because that tells us how much of E is parallel to A. And whatever part of E that's parallel to A, it is definitely going through the surface. So pictorially or geometrically here, that looks basically like what I just drew here, but for these surfaces, for this surface and for this cross-section area. So if I project A out like this, and that's why I wanted to just do one vector. I'm going to go back to just one. That's not confusing. Then basically what I'm doing is finding the part of E that is parallel to A. I'm finding the part of the electric field. I'm dropping this perpendicular back like this. That part right there is going to be E cos theta. And it's parallel to A. You can clearly see it. So whenever E is 0 degrees, cosine of 0 is 1. So you get all of the field going through the surface. Whenever whenever theta is 90 degrees, then E is basically parallel to the surface, and none of it will go through, just like the water dripping down the surface. So when E is constant, then I'm sorry, when E is constant over the surface, then this integral of E dot dA. Well, first of all, you do the dot product. And so I'm going to make, so that's not a really good, because I did make it at an angle. But so the simplest case, I guess, where E is constant and perpendicular to the surface. It's constant over the surface and perpendicular to the surface. When E is constant over the surface and perpendicular to the surface, then you essentially would have a situation that looks like this. This is the surface, and then E would make a 90-degree angle to the surface, which means it would be parallel to A, which also makes a 90-degree angle with the surface. So that's E, and this is A. And so in that simplest case, this integral then, flux equals the integral of E dot dA. But since E is, well, and then that becomes integral of E dA times the cosine of theta, but theta is 0 degrees because E and A are parallel. So cosine of 0 becomes 1. E is a constant. It comes out of the integral, so you just have the integral of E times dA. But the integral of dA is just A, so then the flux then just becomes E times A. The magnitude of the field E times the magnitude of the cross-section area. Whatever the geometrical figure is, if it's a rectangle, then it's going to be length times width. If it's a square, it's going to be length, a squared. If it's a sphere, 4 pi, whatever it is, the flux would just be E times A for a flat surface. Well, for a sphere, actually, excuse me, I meant for a circle. For a sphere, we have to consider something else here in a minute. But for so basically the maximum flux that you can get for a surface is going to be the value of the electric field that cuts through that surface times the magnitude of A. And since cosine technically goes through from 0 to 90, then that cosine theta becomes like a multiplicative factor that takes the flux from 0 to the maximum. So in general, in magnitude, then flux is going to be equal to, I could have kept that in there, I guess, but flux is E times A times the cosine of theta. And that's what I wanted to get back to here, is that the magnitude of the flux is always going to be that. That's electrostatic. So this is sometimes people start with that as a definition, but I like to start with the integral form. So this is for a constant field, you could think of it as just E dot A. So another representation when E is constant is just E dot A. But the most general form of flux is going to be the integral form here. So all those things are the equations that represent electrostatic flux, the magnitude of electrostatic flux. Basically 3 different versions. And those versions are the generalized version here, integral of E dot dA. And then you have the magnitude of, for a constant field, E over a constant over a surface is just E dot A. And then the magnitude of that is E A cos theta. These 3 versions. Now, I guess we got about an hour. I guess I was doing some administrative work there and didn't start class, lecture right at 8 o'clock while I was here. I'm going to take a quick break, and then now that we have flux defined, I have enough information where I can define, I can derive Gauss's law. Oh, one more thing before, well, no, let's go flux inside. Well, yeah, I'll do the flux of closed surface and then we'll do Gauss's law, right? Yeah. Okay. So, let me take a little break and I'm gonna come back. When I come back, we're gonna have a closed surface like this guy. And we're gonna look at the total. So this was the flux of a flat surface. But what about the flux of a closed surface? There's something quite significant about that we'll take a look at when we come back. All right, so that's a good breaking point. I'll take about 10, 15. Okay. So I'm going to calculate the flux of this box, and then I'm going to derive Gauss's law. Once we do that, and I think that'll bring us to the end of class. So flux, even though it's a scalar quantity, it is it still abides by superposition, meaning that if I want to calculate the flux of a six-sided surface, I simply calculate the flux of each side and add them up. So and because it's a scalar, I don't have to do any kind of vector analysis, right? Because you know, scalars you can just add. They don't have a direction. Now, here we have to put some direction on this now. So let me make a coordinate system, three-dimensional coordinate system like so. And I'm going to do it so that I take this box and put it right in the corner, like so that one edge is at the origin 0, 0, 0. Yeah, so I don't know, make this a Y. I'll just stick with my notes, Y and Z and X. So I'm going to take a box, this box, and place it right here in the corner. So it's kind of like this. Okay. Oh, let's say that the box has. So now we're going to have an electric field that's going to point along the x direction. Now that means that it's constant and it permeates the entire space. But just like when last semester, whenever we would draw G just in the corner, like so we knew, so remember, recall that whenever you have the ground, right, and you have an object, a mass that's falling, you know, a height h above the ground, we would place it in a G field. Now, we would represent G like that somewhere in the. Now we know that what that means is G is permeating the whole space everywhere, but you know, we don't want to have to draw that every time. So we just draw G up in the corner, whatever. So in that same way, I'm going to draw electric field E here, and it's in the Y direction. So basically, E is equal to a constant field EY. Well, if I have the unit vector, I don't need the vector symbol here. Yeah, and it's pointing in the Y direction. Right? So that means that it's cutting through this surface. Sorry, not in the Y direction, in the X direction. Sorry. Cutting through the surface, pointing along the X direction everywhere. Now remember, this surface has area vectors that are point. So one point's along Y. Hey, I doing? Yeah, how's it going? The other points along Z, then along X, and then along negative Y, negative Z, negative X, all that, right? And yeah, so we just need to simply go through and do the dot product for E with all those surfaces, okay? Now, I guess I could draw them in, a couple of them. I don't want to get, I'll just do it. So first of all, let's just write out the equation. So the total flux of the whole surface is going to be, so flux then is going to be equal to the summation of the flux of each of the sides. So it's kind of written like that. I equals 1 to N of the net flux, yeah. So basically I've got 6 sides, right? So it's going to be, call that equation 1, equation 2, and maybe sometimes people put a net here. So like net. So the net flux is going to be equal to flux 1 plus flux 2 plus flux 3 plus flux 4 plus flux 5 plus flux 6. Now, I'm going to set my box up here. So size 1, 2, 3, 4, 5, and 6. So 1 is going to be pointing along. So I guess Z is out of the board, so I'm going to point 1 towards you. So 1, 2, 3, 4, bottom is 3, 5, and 6. So that would look something like this. 1, and then 2 is on the back. It looks like 2 is on the back. 3 is on the bottom. 4 is top. What is this? 6? 6 points along the X direction. So that's side 6. And side 5 is on the back surface here too. Okay. I don't know. Kind of hard to see with that, but yeah. So if I go through here, basically side 1 is pointing out towards you, but remember E is along the X direction. So the angle between E and A1 is going to be 90 degrees. Cosine of 90 is 0. So doesn't contribute any flux. And that makes sense because for this side, it's like the electric field is not going through that surface, but is pointing, skimming along the side of the surface. If I were to put an electric field, you know, or indicate or draw an electric field that is near that surface. So if we write all of these terms out, kind of to evaluate them qualitatively, what we have is E net is going to be equal to basically integral of E 1, sorry, EY times dA, basically, yeah, we could do it like this. So EX, keep calling it Y, dot dA, and that's pointing along the positive Z direction. So that would be unit vector K, positive K hat for the A. In fact, why don't I do it like this? So I just say dA and Z. Just so you could associate a side with a area, I'll put this like 1, and then, yeah, so I'll put dA1. Yeah, I'll do the unit vector. So dA1, and then that's going to be along the positive k hat direction. This term, number 2, is going to be the integral of E. So EX is always is not going to change. So dot, but side 2 is negative k. So dA2 negative k hat. I'm just going to write all these out, and then we'll evaluate. Hope I can get all 3 in. So then now we've got sides 3 and 4, and that's going to be the y-axis. So that's going to be the integral of EX dotted into dA4, which is pointing straight up. So that's along the positive j direction. Then plus the integral of EX dotted into negative j. So that'd be side 3. So dA3 negative j hat. Then sides 5 and 6, which are a little bit more interesting. Side 5 is this side, and it's pointing in the negative x direction. So that's going to be EX. That's a that you get some flux there. That's non-zero flux. So dot dA5 negative negative I plus integral of EX alongside 6, and that's going to be dA6 positive I. So those are all of the terms of the flux. Now, for that scenario, all the terms of the flux for that scenario. Now, whenever it's simple evaluation, both of these terms give 0 because the angle between EX and dA1 is 90 degrees. And same thing for side 2. So because of the property of the dot product, that guy is 0 and that guy is 0. Similarly, for sides 4 and 3, same thing, right? Remember, here's our object. Side 4 is the top, side 3 is the bottom. The E field is pointing in the x direction. So the area vector for side 4 has got to be perpendicular to that surface, which is straight up. So the angle between them is 90 degrees. Cosine of 90 is 0. So this term goes out. Same thing for the bottom surface. A is pointing down. Angle 90 degrees between E and A, or dA. And so we get 0 contribution there. So this guy is 0. And this guy is 0. Okay? Now for the last 2 sides, sides 5 and 6, well, E is pointing in the positive x direction, side 5, A is pointing in the negative x direction, cosine of 100, and also E is constant over the surface. So let's take a look at this integral a little bit more closely. If we break it down, so I'll call this equation 4. For that last term here, we've got the integral. Now E is a constant. Well, we have E times dA times the cosine of 180 degrees. And then for the other side, they are parallel, right? This is side 6. A for side 6 is pointing in the x direction, but E is also in the x direction, so the angle between them is 0. So plus integral of E dA cosine of 0. Well, that guy is 1. This guy is -1. E is a constant over the surface because it's constant. That's what we said. And so you have E times the integral of basically negative or dA, and that's a -1 we get out of this evaluation of the cosine, plus E constant out of the integral, E times dA. So basically dA integrates to 1 to A. So we have, remember the negative sign here, we have negative E times A. Actually, it's A 5 and 6, but A5 and 6, it's a box, right? So the areas are the same, it's just A squared for each side. So EA plus EA. So although you do get flux for the individual sides, 5 and 6 respectively, it's the same flux because it's a box and because E is constant. So those cancel out, and you get that the total flux then for this box is equal to 0. The net flux for a closed surface well, we should say that a little carefully. The net flux of an external field over a closed surface is 0 in this case. And in fact, it's always 0. Now, be careful what I said. I said the net flux of an external field over a closed surface, as we illustrated here, is 0, but it turns out it's always 0. Let me write that, and then we'll explain a little bit more detail. The net flux of an external field, I said over a closed surface, but I guess I should say through a closed surface. The net flux of an external field through a closed surface is always 0. Excuse my abbreviation of the word through there, just trying to save myself some time and space. That always felt like a really nice, appropriate abbreviation of that word. External field, meaning that we know electric fields have sources. They are positive and negative charges, right? So when we say this field is, pointing in the X direction, first of all, that's not natural, right? Because charges are point charges. We assume circular symmetry, and you never get a constant field with circular symmetry. So maybe it was a capacitor plate that we set up. Maybe we've got this box immersed in huge capacitor plates that are charged and flat, so they're creating a constant electric field. But the point is that the source of those field lines are not in the box. They're outside of the box. So that's what I mean by external field. The source of the field is outside of the box. Whenever we have a source that is outside the box, the flux is always going to be 0 because whatever flux goes into the box will have to come out of the box because the source is not inside. Think of it like this. What if I made this thing of chicken wire? It was chicken wire, right? And again, I go back to my hose and I have water anywhere. I don't know, it could be anywhere, like a hose, and I'm sprinkling water down. Well, it's chicken wire, so the water's going to go in, but at some point it's got to come out. So whatever positive flux I have in one direction, I'll have negative flux in the other direction, or negative and then positive, whatever. And that's what we're seeing here, specifically with the sides along the x direction, the direction whose area vector is parallel to the external field. That's a simple case. You can make more complex cases where E is not constant, whatever. You have to integrate to all kind of bunches. But in the end, it's just going to be zero whenever the source is outside. Corollary to that is that if the source is on the inside, the flux will never be zero. Well, actually, it could be. It depends on, be careful about that. It depends on whether or not you have the polarity of the charge and whether that they cancel one another out. But that said, maybe it's time at this point, in order to go further and illustrate that part, is to derive Gauss's law. And I think we have enough information to do it at this point. And so I'll derive it, and then on Wednesday, we'll work problems. So Gauss's law. So this was flux, and this lecture that we just finished was all that was about flux. I know I got 5 minutes here, but nobody's in class, so I'm going to go over a little bit, I think, and get this done so that we can just work problems on Wednesday, and then introduce the concept of electric potential by the end of class. And that's what I would want to do this week, and we're back on schedule if I can get that done, is Gauss's law and introduction of electric potential. And we'll continue with electric potential into next week. Also, I didn't post your test this weekend, which somehow I had a brain fart. So I'm going to scroll that back and post it this week. This is the test for chapters, the first 2 chapters. I was supposed to do that. I thought I did. I guess I did for the other class and forgot I didn't do that for this. I don't know. But I will post it for you. It just gives you more time to kind of get the homework for study and stuff. So, but I will, and also probably give me a little bit more chance to do some problems and post them. I didn't do that with this class this weekend as well. But yeah, so what am I doing? Gauss's law. Yeah, so let's derive Gauss's law. And to derive Gauss's law, we simply calculate the flux of a point charge, a distance r away from the surface of the point charge. Let's go ahead and take a positive charge. Consider that. Gauss's law. And this is Frederick Gauss, I think, and he lived, he was one of these 17th century mathematicians, contemporary of, I think he might have been contemporary of Isaac Newton. It's Frederick Gauss, maybe 18th, was it 18th or maybe 18th century? Yeah, 18th century. Let's see. What does this do? Yeah, okay, not bad. 1777 to 1855. So 18th century dude. And it's Frederick. He's got a long name, but I think let's just say Frederick Gauss. Got a bunch of middle names. Carl Frederick Gauss, maybe that's it. Yeah, Carl. I think he was Swiss. In 1777 to 18. 55, so you had a pretty good. Moved into his 70s or 80s. What is that? 55 plus 13, 78. No, 68. 13, 20, no, 23, not 13. So yes, 78. Um, yeah, so positive charge. Consider a positive charge of charge plus Q. Positive point charge. Q plus. Now we know this field. Sorry about that. So positive charge. Have to get my ink straight. So we've got the field lines that radiate, as we know, radially away from the charge. The field lines are going to be doing this. Of course, they terminate on the charge, coming all the way in. That's definitely not a constant field. You see that the field, and we know the field goes as 1 over r squared. It decreases as you move away. And so the density, because the field magnitude decreases, and as we said earlier, it's because the field intensity or magnitude of the field is proportional to the line density. We can see that as you move away from the charge, the space between the line increases. The same number of lines represented here are 8. So that doesn't change. So the number of lines per unit area, or whatever volume, if you want to think of it three-dimensionally, is definitely going to decrease. So our objective here is we want to figure out the flux through some surface a distance r away from the point charge. So find the flux, the electrostatic flux. Doesn't have to be capitalized. A distance r away from Q plus, meaning the center of Q plus. I've been using this word a lot, electrostatic. What does that mean? It's not just that it's constant in space. It really means it's constant in time. So in fact, it's not constant in space. It's changing, right? The field, but it has a certain field pattern, it's a radial field pattern. What we're really saying is the field pattern itself is not changing. So something that would be representative of a constant, a field that's not static, is if I took this charge and I shook it. As I shake, basically that would create an electromagnetic wave, to be honest with you. But the way that I think of it is kind of like this: is if you have a field, a charge associated with a charge, and has a field, you can kind of think of the analogy that I have in my mind is a spider web, right? Now spiders make their webs two-dimensionally. Usually, they're not. That'd be really weird. Wow, I never thought about that. What if a spider made his web three-dimensional web? They don't. They're usually two-dimensional, right? It's something like so you have some central lines going out radially away from the charge like that, and then you have something that does this, right? It connects them. What we'll see is that the radial lines are like the E field, and when we get to the magnetic field, I'll make an analogy to say that the lines that connect are kind of like the B field, because we'll see that B field and E and B field of the same source are always perpendicular at every point. Anyway, let's just deal with the E field right now. So if I had something that were just like going out, an E field that was kind of radiating out like that, basically if I shake it, I'm going to create a wave on the thing. Like if it were a spider web and it was connected, if I hit the center of it, it's going to, send out, it's kind of like dropping a pebble in water. The spherical waves go out on the surface of the water. Here, in the case of the spider web, spherical waves would go out radially on the web. Here, it's 3 dimensions, so it's a sphere. Spherical waves propagate out. If I shake it or disturb it, flick it, something like that, spherically on the spherical wave fronts would propagate out on on the fields, on the electric field and also magnetic field pattern that would be there prior to the disturbance. So when I say electrostatic, what I'm saying is that it's not changing in time, the field, and therefore whatever the field pattern is at an instant in time, it's like if you take a snapshot of that, that would be the static field. But if the field doesn't change, then it maintains that pattern throughout space and time, and it doesn't change. So that's, I'm basically, electrostatics and magnetostatics deal with fields that are non-time varying. When we get to varying electric and magnetic fields, those are actually electromagnetic waves. And so we'll talk about that when we get to that. So the static field. So the flux then, it's about flow, the flow of the pattern. So if I'm a distance r away from the center of this distribution, that's where I want to find the flux. That point P. That's that distance away. Now, it's a spherical distribution, so it really, if you were to think about that point at position r becoming a sphere of radius r, then that sphere becomes a surface, really a closed surface about which I want to determine the field. Because it's going to be, whatever the flux is, it's going to be the same flux because the field is uniform, not constant, but uniform is what we say, because it is changing its magnitude. But because the field pattern is not the same and because it's symmetric and radial about the center, then for this particular distribution, the amount of the magnitude of the field that cuts through a point at radius r is going to cut through, you can create a surface at which that's the same amount of flux everywhere on the surface, because E everywhere on the surface is the same value. So E is not constant, it's changing, but for this surface at a distance r away, if the charge is centered about that surface, then E is constant over that surface. Now, this sphere that I've drawn, it's a tool that we use to basically do what I just told you, to illustrate what I just said to you, and more that we'll show in a minute. But this has a name. It was created by Mr. Gauss, and we call it a Gaussian, we refer to it as a Gaussian surface. It's a theoretical mathematical construct that we just use, and we can manipulate it, shape it into whatever shape we want, and we generally use it to determine the flux associated with the charge distribution. So it becomes a tool. Because if we're going to calculate flux, even if there's no actual surface there, we definitely need a surface, because otherwise there's no flux, right? In the definition of flux, there's E dot dA. So there's an E, but if there's no A, then there's no surface for the electric field to flow through. So obviously, trivially, the flux would be zero in that case. So even if there's not a surface there, we can make one up theoretically, mathematically, in order to evaluate the flux. So that's it. That's the Gaussian surface. It's a closed surface always, for the purpose of our case. A Gaussian surface is a closed mathematical surface used to basically evaluate the flux of an electric, the flux about a charge distribution. So that would be my definition. Let me go over here and define it. So a Gaussian surface, or Gaussian, not to be confused with the the Bell distribution of the same name, same mathematician, Gauss. You know, the bell curve, that's also called a Gaussian distribution. And so Gauss is the guy who did that as well. Pretty prolific dude for his time period. Obviously, you know, 300 years later, or no, what? Wow. 600, almost 700 years later. We're still talking about it. What was I doing? Oh yeah, Gaussian surface is a closed mathematical construct, a closed surface. So a closed surface closed theoretical construct. And in parentheses, I put surface. Used to visualize well, you can't really use to basically evaluate, yeah, and visualize flux because it's a scalar. Evaluate, could visualize the electric field in the area, but not the flux. So Gaussian surface, a closed theoretical mathematical construct, surface used to evaluate the flux associated with a charge / mass distribution. Because as I told you, you can also derive Gauss's law for gravity, which I will do. I'm going to do this. So that's what a Gaussian surface is. So sometimes we loosely refer to it as a Gaussian, and when we do, we don't mean a bell-shaped curve. We have to use those. You have to remember the context. So we're talking about this thing. So there's a little bit of an art or finesse to using a Gaussian. One of the things I've done here is I've chosen the geometry of the Gaussian to match the geometry of my charge distribution. Because I could write these points here because they're important. You know, ideally, Gaussian characteristics, Gaussian matches the geometry of charge distribution, let's say. Now, the reason that's nice, and I say that because here, my charge is spherical, my Gaussian is spherical. I've centered my charge, you know, on the, you know, or I've basically created my Gaussian such that it's at the charge is at the center. And what that means is that every place the electric field cuts the surface, it's going to cut the surface at a 90-degree angle to the tangent of the surface at that point, or tangent to the surface at that point. So that's nice because that makes the flux integral easier to evaluate. Not only that, because it's centered, as I said earlier, a moment ago, I know the field is decreasing, but it goes as 1 over r squared. So if I'm the same distance, away from the center of charge distribution, the magnitude of E is going to be the same. So the direction is always perpendicular for every electric field vector that crosses the surface. So the angle is 90 degrees everywhere, but the magnitude of E is also 90 degrees everywhere. So by choosing that symmetry, so that's the kind of thing I'll see many examples as we work on them even into Wednesday. But that's the beauty of Gauss's law. You only want to use it when you have high symmetry or create high symmetry. You don't want to be asymmetric because otherwise you then have to, that integral, the E dot dA integral becomes extremely difficult. In fact, because you got a cosine in it, right? So which could change. So that integral actually becomes more potentially harder than Coulomb's law. So if I were going to integrate, I might as well just do, KE, KQ over R squared, what we've been doing the past, last week, as opposed to, doing Gauss's law, then having to integrate something raised as well. So usually when we're using Gauss's law, we're going from Coulomb's law, harder mathematics, to simpler mathematics. But there's a trade-off, and this is probably I would postulate this as I see this in physics everywhere, and then maybe it's part of the universe, that the more elegant the equation that you have, obviously the more powerful, but the more, and that's what definition of elegance, in my opinion, is something that you get more information out of the same or even less criteria or less wording. So that's why poetry is more powerful oftentimes than prose, because you can store information in the meter and the rhyme and all that stuff as opposed to just the words. So you can say more with less. So same thing in physics. An elegant equation is an equation that packs much more in terms of the implication than is obvious. Like, for example, E equals mc squared, the most famous equation in the world. But Gauss's law, probably before that, Gauss's law probably was the most famous equation. The Gauss's law for the various, the various fields. Digress a little bit, but my point is that I've got high symmetry here, so let's exploit that. Because now I can just work out, I can evaluate the integral. So let's do so. So if I find the flux now, E is equal to the integral. I always like to start from the most basic definition, even if it's maybe overkill. So this becomes integral of E dA cosine of theta. But everywhere here, I just showed you, my theta is 90 degrees. Sorry, it's 0 degrees. Did I say 90? I did say 90, my bad. It's 90 degrees relative to the tangent, that's true. But the area vector everywhere is also perpendicular to the tangent. So that's A and that's E. So everywhere, basically E and A are parallel for this symmetry. Let me not, hope you don't get that twisted. Yes, it's true that E is perpendicular to a tangent everywhere that E crosses the surface, but A is also perpendicular to a tangent everywhere that, everywhere on the surface, because that's how we define A. A is perpendicular to the surface that it describes. So that means that E is perpendicular to the surface and A is perpendicular to the surface, they're parallel to one another. So the angle between E and A, or dA, is 0. Now, what's the difference between A and and dA? I said it, but I think I have enough here to illustrate it. Basically, dA is a differential element, right? It's like if I were to pick out a little block here on the surface, it might look like that.
So that's not the whole area. That's not the 4 pi r squared. That's just a little differential area. And its vector is going to point up perpendicular to that space. And its magnitude is just the d, well, d, it's in spherical coordinates, but it would just be the area associated with that little space thing. Right. So it's that area that I'm finding the electric field in association with. Now the electric field is still going to come through and be radial. And then so it's still going to be, E is still parallel to dA. So there's still 0 degrees between them. So as I said, E is constant. It comes out of the integral. So we really then just have E times the integral of dA. And again, this is a triple integral, that dA. But we don't have to do it because we know what the area is, area of a sphere. We already know what it is. So we just use it. So it's 4/3, 4 pi r squared, as I said. So yeah. So that's the area of a sphere. So that, in fact, let me number these quickly. 1, 2. Okay. Let's continue this over here. Sorry, I had a brain fart there for a minute. So the flux E is equal to, now here's the thing. We know what E looks like. We did that all last week and the week before. That's a point charge. So E is KQ over R squared. So K, the Coulomb constant, Q, the value of the charge, that's Q plus over R squared. Okay. But then the area of a sphere, let's call that E A for a sphere. The area of the sphere is 4 pi r squared. 4 pi r squared. So that when you work this out, what you see is that the r cancels, r squared cancels. I've got a 4 pi left. Yeah. So but remember, K is 1 over 4 pi epsilon naught. So 1 over 4 pi epsilon naught times Q plus over 1. And then times the well, let's just keep the squared in there for now. Whatever. So yeah, 1 over 1. And then the 4 pi. Well, now you see that the 4 pi cancels. And I'm left with the result. The classic result is that the flux through that surface is equal to net flux is equal to Q plus divided by epsilon naught. Now, it's a little bit hard to show here because this is just a specific example. But if I did several examples, kept doing this, what it would show me is that if I had more charges here, like, if I took a charge and I, had maybe a negative charge, then same, minus Q, another 2 plus, I don't know, whatever, just basically Gauss's law, this is showing that Gauss's law the flux only depends on the amount of charge inside, and the permittivity of free space. And the interesting thing is that you see over here, there's no geometric terms here. So although I needed to rely on high symmetry by centering this charge within my Gaussian surface, in the end, there's nothing about the result of the flux that indicates the geometry or the symmetry. So in fact, the symmetry was just helpful for me to work it out. But if we were to do various examples, even ones where we might have to integrate a little bit and we couldn't just simplify with symmetry, in the end, we still see the same result, that the only thing the flux depends upon is the magnitude of the charge inside the Gaussian surface. And it does not depend on the position of the charge within the relative position of the charge or charges within the Gaussian surface. So ultimately, Gauss's law becomes a very elegant and powerful equation because we can generalize to say that the net flux over a closed surface is equal to the summation of the charge that's inside. So we say net charge enclosed, so ENC means enclosed, divided by the permittivity of free space. And we're assuming all this is in a vacuum. If it's not a vacuum, then epsilon changes. But yeah, so that's it. That's Gauss's law. So what that is literally saying is that we don't have to do this process anymore. If we have so really reinforcing the power of Gauss's law, let's say that I have several point charges in a region. So +2 coulombs, and then -3 coulombs, and then +5 coulombs. And I have some Gaussian. And here, the Gaussian doesn't even have to be, I'm just going to do some arbitrary, shape. That's my Gaussian. And it's enclosing that charge. Well, use Gauss's law to determine the flux through that surface. Here's my Gaussian here. Well, the beauty of Gauss's law is that I don't have to do all that stuff I just did. All I got to do is add up the charges, just basically apply this equation. The flux of that surface enclosed is going to be, well, the net flux of that surface is going to be the total charge. That's going to be 2 coulombs minus 3 coulombs plus 5 coulombs divided by epsilon naught. So the total flux over that surface is just going to be I can't add. +4 epsilon naught, +4 coulombs up. So flux, and we have to do the units. So +4 coulombs over epsilon naught. Epsilon naught has a value, so we have to work it out. I mean, I could give that as the answer, but technically, the units for flux is going to be the units for electric field times area, units for area. Unit for electric field, you could, at this point, let's just say it's Newton per Coulomb. So a Newton per Coulomb and meter squared is going to be the units for that. So, and it doesn't have a name. So the overall units would be Newton per Coulomb, Newton meter squared per Coulomb. So I offered you to work out that those units work out. Like for epsilon naught, what do we say epsilon naught is? It's 8.85 times 10 to the negative 11 or no, yeah, because K sub B is 8.99 times 10 to the 9. Epsilon naught is something like that. Let me just do my notes here. I'll do it. And I'll see that in the first one. Mm, mm. Just get that and then we'll finish up. Yeah, add negative 12. 8.854 times 10 to the negative 12. And that's going to be yeah. So Coulomb per Newton meter squared. Sorry, Coulomb squared. Right. Yeah, so in this case, the flux would be 4 divided by that number. And of course, that's charge. So you could see one charge there is going to divide out a Coulomb squared in the denominator, and that would give you, so these are the right units for this, for flux, but for Coulomb. So this is Newton meter squared over Coulomb, and this is Coulomb squared over Newton meter squared. That's right. Yeah, yeah. So that's Gauss's law, folks. Now, what's nice is that we'll get to this on Monday. On Wednesday, need to remember to derive so I would encourage you to see if you can replace everything where there's a C or a Q, replace it with M, and try to see if you can derive the Gauss's law for gravity. Keep in mind that if you start, there's no source for gravity, but if you assume that there's a small point mass, then we could kind of make an analogy between that and this problem where the gravitational field is also radial, but it points in toward the center, as opposed to out radially. It points in radially toward the center of the mass distribution. Now, again, this is not a source we don't think of, because we haven't found any gravitational monopoles. But you could, we know that the Earth is circular, the sun is circular, the moon is. So if you had a very small mass, like maybe a proton or something like that, its gravitational field would look something like that, and you could go through the same steps that I did to derive the Gauss's law for gravity, and go ahead and do that, and see if you can, or you could, yeah, go ahead and do that as an exercise. And for any problem that we do with charge, as I said, just like with Coulomb's law and the universal law of gravity, we can do with Coulomb's, with Gauss's law for electrostatics and Gauss's law for gravity. So I didn't do any spherical problems for you with Coulomb's law. I have them in my notes, but it's like a 3-page problem because it just gets more complex. So just in expedite the lecture, I usually just wait until I derive Gauss's law. Then on Wednesday, we'll use Gauss's law. In fact, this is spherical symmetry, right? We'll use Gauss's law to figure out the the electric field for charge distributions. And in case you're wondering, I'll do one last example, then I'll let you go. I know that I used a point charge to figure out Gauss's law, but now I can use Gauss's law to figure out the field of the point charge. Basically what I just did here, I used Gauss's law to figure out the flux of this surface here, which is going to be a bunch of problems that will give you that. But the last thing that I want to show you is that, and that's the purpose of Gauss's law, is really the easier ways to find the field. And I know it's going to look like kind of redundant because this is the simplest example, but now I'm going to take this law, apply it to this scenario, and show you that you're going to get the field that we expect, namely KQ over R squared. Use this space. It looks kind of trivial in this example, but it's not actually. It's pretty significant. And we can use it for more difficult distributions. Anyway, so we have a point charge, and we want to find the field at distance r away from that point charge at point P. Okay. Find E. And again, this is, find E at point P. So the method is that, first of all, evaluate the charge and evaluate the charge distribution. So, in fact, I might put steps for Gauss's law or applying Gauss's law. 1, evaluate the charge distribution. Charge or mass. Next, which goes right along with that, evaluate the field pattern associated with that charge distribution. In this case, my charge distribution is circular, so my electric field is radial, pointing away from that charge. Okay, so that's E. Next, choose your Gaussian surface. And it has certain criteria. Choose Gaussian. And the criteria basically can be broken down into 2. 1, we want high symmetry. And by that I mean, generally, if you choose a Gaussian that is symmetric, that is similar to the geometry of the charge distribution, then that's the symmetry that you need. And center it whatever you need to do to center. Usually that's also, so symmetry, centering, and when you center, basically, well, not necessarily centering, but usually that's what you have to do, but you want to make sure that you choose the Gaussian and position it in such a way that, if you can, that the electric field is constant over the surface. So E constant relative to, constant Just say over surface. Okay. So in this case, we're going to do, we'll take it here, and we'll make our surface, our Gaussian surface will be like a sphere, and its radius will be r. So wherever we choose the Gaussian, wherever we place the Gaussian, that's where we're going to find the field. So we want to make sure that if we are finding the field at a particular point, we make our Gaussian big enough such that at least part of the surface goes through that point. So we choose our Gaussian and then apply Gauss's law, I guess. So 4 steps. Choose Gaussian, make sure that the point goes through the surface, whatever. I think we need to write that, and then apply Gauss's law. Okay, so Gauss's law says that the net flux over my Gaussian surface has got to be equal to the total charge enclosed inside divided by epsilon naught. Okay, so this is an integral. So that's going to be the integral. Now here's the thing. With Gauss's law, Gaussian surface is always a closed surface. So it's not just, so when I do this integral over here, you're going to see some symbols, mathematical symbology symbols, where you have a circle on the integral. And usually it's an S. You have like a script S down there, which means surface, because there are other integrals where you have to do a closed integral, like you can do it in a 2-dimensional plane, which would be a contour. And so that's something else we'll do for magnetism. But anyway, there you would see a circle and a C. This is a circle and an S, meaning the surface is closed. And so that's now E dot dA equals total charge enclosed divided by epsilon naught. I'm going to keep with my numbering here. So just equation 7 and then equation 8. Keep those criteria there, and we'll come over here. Now, I'll evaluate the left side first. Now, because I've chosen my Gaussian to be highly symmetric and everything, this integral becomes simple. One, I don't know what the value of E is. That's what I'm trying to figure it out. But I know that everywhere on the surface, it's constant. Why? Because of all the things we said the whole class period. That now that I've chosen this thing symmetrically, E crosses, it's 90 degrees to the tangent to the surface, which means it's parallel to A at that point, and everywhere it's the same. So E is a constant of the integration. So, well, I'll go ahead and evaluate it first, evaluate the dot product. So that's going to be E dA times the cosine of 0 degrees, everywhere is 1. That equals the total charge enclosed divided by epsilon naught. Okay, so I'm just writing that down, keeping that going until I get to that in a second. So E is it's a constant over the surface. So it comes out. So I have E times the integral over a closed surface of dA, right, equals the total charge enclosed divided by epsilon naught. Okay. Well, what is the integral of dA? Well, this is a sphere. It's not a circle now. This is a sphere. And, you can either look that up or, and so for these geometrical figures, you want to know what the area and volumes are for like a sphere, rectangular shape, and a cylindrical shape. Those are the basic geometries that we'll be using here over the next couple of weeks. So in this case, the sphere and the area, not volume of it, but area of a sphere is 4 pi r squared. So, and where r is obviously the radius of the, now be careful, that's another thing. This is the area of the Gaussian. So again, this is a point charge, so it doesn't really have any shape, But we're going to do problems on Wednesday where we have a shape, a spherical shape that has a non-zero radius. So don't get it twisted. The area in the left side of this equation is the area of the Gaussian, not of the charge distribution, always. Now, sometimes the charge distribution, if it's a sphere, you can lay the Gaussian right over the surface of the charge distribution. So in that case, the radius of the charge distribution and the radius of the Gaussian are the same thing. But ultimately, the formula, the application of Gauss's law, dictates that when you evaluate the integral on this left side here, the area is always the area of the Gaussian. If that just happens to be also the area of the charge distribution, fine. But it's not defined to be that. It's not going to be that always. So anyway, this becomes the area of the Gaussian. So that's E times 4 pi r, r squared. Yeah. And that equals the total charge. Now I can evaluate the left side. How much charge do I have enclosed inside this Gaussian? Well, it's just Q, just positive Q. So it's just going to be plus Q, or Q plus over epsilon naught. And again, the unknown is E. I'm trying to find the field at that point. So I just solved this for E. And what I see is, voila. 1 over 4 pi r squared times Q plus over epsilon naught. If I what's that term, that property? Commutative, distributive. I guess it's commutative, huh? No, distributive. Distributive. I can't even remember them. But anyway, I can rearrange this. I think that's redistributed. So take epsilon, put it in 1 over 4 pi epsilon naught, and then put the r squared under the q. So q plus over r squared. Then rewrite. This thing is k. So k to b, and then q plus over r squared. How about that? Is that a surprise? No. That's what you would expect, because that's what the field of a point charge is, kq over r squared. So Gauss's law basically is an alternative method of finding the electric field of a charge distribution, provided that we can either exploit symmetry or it's just obviously symmetric. Otherwise, this integral is not simple. Like whenever we do apply Gauss's law, right? No matter how complex the charge distribution, if we do it right and it can be applied, the left side is going to be like this, where stuff goes out and we get a simple, basically not even working really out the integral. If that's not the case, then this becomes a very difficult integral, right? Because theta could change, E could change, D. I mean, and my point, I said it earlier, I'll say it again. And it's a closed integral. I mean, it's crazy. It's like if I was going to do all that, it's always going to be a triple integral because you always have a surface. If I was going to do all that, I might as well just do Coulomb's law, right? Coulomb's law isn't that complicated generally. But, it's complicated enough. We did that. We showed you last week, but, but, sometimes maybe it is a way. I mean, like whatever. So that's it. That's Gauss's law. That's Gauss's law. So we're going to apply this to a lot of problems where next week, in different types in your book, in the chapter, where, you could very quickly see how difficult using Coulomb's law would be to figure out those electric fields. I have to say, I think this course is probably when I really fell in love with physics. I had chosen, I think I mentioned to some of you that I was kind of intimidated by physics. In my first semester as a freshman, I chose engineering, I think civil engineering, because I just was intimidated by physics and thought it might be able to do it. But then I got into the engineering course and realized for the next 2 years, I'd be taking the same courses as the physics students, with the exception of,
introductory. I think we had drafting or something back then in civil engineering. I was like, if I want to be doing it, I might as well do physics. So I switched over and never turned around. But that first 2 or 3 semesters, first 2 semesters, I was pretty intimidated my freshman year. But then I got to this semester, and I had a little difficulty with the integrals too. You know, it's straightforward, but it's integration, so I wasn't very good at, as good at back then at math as I am now. But you know, it's math, right? So if you figure it out, you know, you can do it. It's not the physics. But it wasn't until I got to Gauss's law, for some reason, this just clicked with me. Like I was like, yeah, I really got it. I could see it, all the stuff. And, you know, you start to use Gauss's law and you compare it to like using Coulomb's law. And it's like night and day in terms of the difficulty, Gauss's law being much easier. And it just really inspired me that just for a lot of reasons, you know, I could go on, I could talk for probably several minutes about this, but it really kind of kicked me in gear to really try to understand, and, you know, it inspired me and I was motivated. So even though I guess physics didn't really get less difficult for me, it got more enjoyable, I would say, because I could understand something that's pretty esoteric, and it just gave me a different perspective about what physics is and what the kind of difficulties that I was having and why. It had nothing to do with my ability to understand the physics, but maybe other things that I had to clean up. So anyway, that's Gauss's law, and I will open the homework 3 and on that stuff, and also we're starting to do some labs now. I've assigned lab, the first Beyond Labs lab for this course, and I will get your test posted so that I'll think about probably today, and I'll think about like how to I'll give you a couple of days, like the same amount of time that I would have given you if I had opened it up on Friday, and it would have been due probably today or tomorrow. I'll do the same thing. Maybe we'll do it for the weekend. All right. So yeah, class dismissed. And cool. Start reading through. I guess this is the next chapter, 23, I believe. All right. Yeah.